So electrostatic interactions is sort of a blanket term to kind of describe all the others. The definition of electrostatic is really straightforward. It's charge that isn't moving. Electro, charge, static, we're not moving. Okay? Dipole, a separation of charge. Okay? Again, pretty straightforward. So then examples of electrostatic interactions or noncovalent interactions, your textbook will use these words interchangeably. I will also use them interchangeably. This is just a good maybe point to have a side comment, since so many of you are in biochem. Some of the things I say will not be the same as the way they decide to say them in biochem, or the terminology used in the text might not be exactly the same. I need you to just stick with what we're doing when we're here. I know that that can be frustrating. It especially gets frustrating when we start talking about sort of this biological typical state. I'm going to say we're always at 310 Kelvin, we're always at 7.4 pH, and sometimes they'll use something like very slightly different. I'm going to say we're always at 1 atmospheric pressure. Biological standard state, if they use something different, you just got to separate the two courses. Okay, so we can have van der Waals interactions, we can have an ion pair or salt bridge, hydrogen bonding. Steric effects are generally going to be repulsive. We're talking about physical interactions between these two things based on their distance apart or their size. And any of these interactions could be attractive, meaning two different charges are coming together, or repulsive. So van der Waals interactions, we have some sort of isolated neutral atom. If we bring it into the general region of some charge, any charge, we can induce a dipole in it, okay? And we can get it to have some sort of separation of charge, some induced dipole, positive on this end, and negative will orient itself towards whatever we've brought towards it, this positive charged unit. Another option is that spontaneously, just by random stochastic chance, an atom will have a distribution of charge, will create a dipole, and then it can induce a dipole in the atom next to it, so on and so forth. So just random fluctuations and distributions in the electron cloud can result in dipoles, or forget can, they do. This will happen. So here is our energy distance plot for a van der Waals interaction. The thing to note, before we were looking at hundreds of kilojoules per mole as our scale for our energy. Here we're talking about, what is this, like 2? This is a really, really weak interaction, okay? I won't actually use this term at all, the sum of the van der Waals radii. I won't use that phrase. Okay? But again, we have maybe two dipoles interacting with each other, and there's going to be some distance between them where they're at sort of their lowest energy, and this is where a van der Waals interaction is occurring. However, thermal energy at room temperature is even lower. So what does that mean? What is thermal energy at room temperature? What are we talking about? What's the other one besides potential energy? Kinetic. Okay, so temperature is a measure of kinetic energy. We always have temperature. We're always going to have kinetic energy. We're never operating at absolute zero. Like I said, we're caring about stuff in the body, so we're pretty much always operating at 310 Kelvin or 37 C. It's the temperature we care about. Basically what this means is that random motion, through the fact that we have kinetic energy, we have thermal energy resulting from being at room temp or higher. As things collide, we're going to break van der Waals interactions. Van der Waals interactions are so weak, they're very transient. Simply through random motion, they're going to break and form. So just easily broken through molecular collisions.